Hello all of you. In the last lecture we have been discussing the canonical ensemble and how can we compute the properties using the partition function. And finally we discussed the example of an ideal gas partition function and how can we derive the equation of a state of an ideal gas. So in this lecture we will take the argument further and we first discuss one more example, that is the Wonderwall's equation of a state, that is true for dense gases. And then finally I will discuss how to do it for the grand canonical ensemble, that is when the chemical potential are the control variables, that is like an open system kind of an arrangement. So essentially this is where we were at. So we are doing the ideal gas case and I defined the partition function of an ideal gas. I didn't derive it. I told you that to derive it, it has to be a different kind of a theory, but we had some intuition that since the particles can pretty much be anywhere in the volume V, so there are almost like V ways, or the number of ways of placing one particle is proportional to V, that is the volume. And so if I have n particles, we have V to the power n number of ways of distributing it proportional to that, and then there has to be a function of t. If one does the derivation for an ideal gas, it turns out that the function f t is given by this, and using that we already have established that if I do, for example, dou ln q by dou v, what do I get is beta p bar, which in this case was something like ln q was n ln v plus ln of f t. The second term does not contribute to the derivative with respect to volume. So what I essentially got was dou ln q by dou v is equal to n by v is equal to beta p bar, and that gives me PV is equal to n kBT. So now we can also find other properties using the ideal gas model. For example, if I am interested in the average energy of an ideal gas, that is given as we discussed, minus of dou ln q by dou beta, and in that case the function of f t has to be differentiated with respect to beta. So we will do that in a minute. But then we can also extend the ideas to other kinds of gases for which the ideal gas model is not true. For example, one of the model for a dense gas is the following, where q is given by this. The function f of t remains the same if the gas is monoatomic, and the same is true for the ideal gas as well. Only for the monoatomic gas we have this particular function. But then if you look at the first and second term, that is quite complicated than compared to what we had here. And the reason is, in a dense gas we no longer assume that the particles are of 0 size, they occupy some volume. Roughly speaking, B is the volume of one particle, and therefore once I place that particle, that volume is occupied. So the other particle can only come in the other part of the space, not in that space, and therefore the number of ways does not go like v to the power n, it goes to a lower number, that is something like v minus nb to the power n, and all of this is true only when n is large. Then there is one more factor, again I am not deriving how it is coming, but essentially it is coming because of the fact that the molecules cannot really overlap, or the particles cannot really overlap. That also gives some penalty when this overlap starts to occur, that is, it is stopped as soon as there is an overlap. So we will not really go into the details right now of how it is derived, but just for this value of q also we can compute the property. So let us first start with the equation of state for a dense gas model. So, my Q is now V minus NB to the power n exponential of a n square by V kBt multiplied with some function of t as we had right here. So, now if I am interested in the average pressure is again given as the dou ln q by dou v, but now it is beta multiplied by that, whatever we used for the ideal gas model. And now again we can do the ln q using this. So, ln q in this case will be ln q is n ln v minus nb plus a n square by v kBt plus ln of Ft. So, if I take this derivative with respect to volume, what I get is n by v minus nb minus a n square by v square kBt. Now, since beta is 1 by kBt, on the left hand side we have P bar by kBt. So, I can move the second term to the left hand side, and what I get is P bar plus a n square by v square, and I will move the kBt to the right hand side, and we have n kBt by v minus nb. And if I now move v minus nb to the left hand side, what I essentially get is known as the Wonderwall's equation of state. So, if I compare with an ideal gas model, so for an ideal gas it was P bar V is equal to n kBt, and this dense gas is represented using the Wonderwall's equation of state. If I compare these two, you see that the right hand side is the same, but on the left hand side we have some correction to the pressure and some correction to the volume, and the correction to volume is coming because now we attribute some size to the particles. So, every particle cannot just be anywhere, they only will be in the places where other molecule is not coming, and because of that there is also some repulsion between the particles, or we cannot allow overlap of particle, and that also gives me an additional pressure, so as to speak. What is interesting about this Wonderwall equation of state is, as we will see in the later part of this course, is that if I simply account for this particular correction, this model of the gas can also liquefy. That means, I can show that if I lower the temperature, this thing will go from a gas state to a liquid state. So, as you know, in liquid state you have lesser entropy than compared to gas, and then there is more structure, so as to speak that there is more interaction between the molecules that result in the liquid phase. In the ideal gas model, since we start with assuming that there is no interaction, there is no difference, so as to speak, between a gas state or a liquid state, or in other words, we cannot describe the gas to liquid transition, because the interaction that will appear when the gas becomes liquid is simply not accounted for in the model. However, in this case you have an interaction, even if the interaction is only resulting when there is a close contact or an overlap, even that itself is sufficient to explain the liquefaction of a gas. So, we will come to that point again, but keep in mind that this particular model is also referred as a hard sphere model, and this becomes particularly important when we are doing molecular simulations. This particular model can explain the phase transitions like gas to a liquid and so on. In fact, one of the first computers or supercomputers in those days were used to perform molecular simulations on these hard sphere systems containing barely 200 particles, and even that was, I would say, very big discovery back in those days, because it shows a potential to get equation of state using molecular simulations. So, we will come back to this model also in the molecular simulation part of this course, but keep in mind that we are not really deriving the partition function in all these cases. I simply start with the partition function. The derivation of partition function itself is a whole different story. But once we have partition function, we can get the equation of state. Not only the equation of state, we can also get properties like average energy and specific heat. So, we already have seen that my average energy is given as minus of dou ln q by dou beta, and now the q for an ideal gas, for example, was Vn f of t. We will do the Wonderwall's case a bit later. So, for ideal gas, q is equal to v to the power n f t, and now if I am interested in the derivative with respect to beta, in that case the derivative of f will come into picture, because temperature essentially is related to beta. Beta is equal to 1 by kBt. So, therefore, let me write the form of my ft from what I have started with. So, ft is 1 over n factorial 2 pi m kBt by h square to the power 3 n by 2. That is true for a monoatomic gas. And now if I do dou ln q by dou beta, I can also write this as dou ln q by dou t divided by dou beta by dou t. Now, dou ln q by dou t I can find from here. So, the ln q becomes n ln v plus ln of f, and f, if you look at it, since I am interested in only the temperature, that will only give me a derivative with respect to beta or temperature. Everything else is a constant here. M is the mass, n is the number of particles, h is the Planck's constant, kb is the Boltzmann constant, and therefore, I can write this as some constant, that is a function of n multiplied with t to the power 3n by 2, and therefore, ln of q we will have additional term ln of g, that is the function of n, plus 3n by 2 ln of temperature. So, now if I compute the dou ln q by dou t, what essentially I will get is the first term will not contribute, because now I am taking partial derivative with respect to temperature. So, the volume is held constant here. So, essentially what we have, and the second term also will not contribute, because n is held also constant. So, essentially you will have only the third term contributing, and that will give me 3n by 2t, and dou beta by dou t is, since beta is equal to 1 by kBt, it is minus 1 by kb t square, and this gives me minus 3 by 2 n kb t, and that is equal to minus of E bar, because dou ln q by dou beta is minus of E bar. So, E bar for a monoatomic ideal gas is given as 3 by 2 n kBt. So, let us say if I am now interested in the specific heat. So, the specific heat, as we have discussed, is given as dou E bar by dou T, that is the definition of specific heat, and since we are doing it at constant volume, so it is specific heat at constant volume. Actually, it is the heat capacity, I am sorry, not the specific heat. When I define a specific heat, it is per unit number of particles. In this case, we are doing the heat capacity that is extensive in nature, it depends on quantity. So, E bar we already have seen, it is 3 by 2 N kBT, and therefore, CV is given by 3 by 2 N kB. We could have also got it starting from the partial derivative of the partition function, then we will have a second derivative of the ln Q with respect to beta, giving me the specific heat. That is what we did in the last lecture. So, now let us do the same thing for the Wonderwall's model. So, in the Wonderwall's model, my Q is V minus NB to the power n multiplied with exponential of a n square by V kBT multiplied with the same function f of t, and f of t I already have written as some function g of n multiplied with t to the power 3n by 2. So, if I do a ln Q here, what I essentially have is n ln V minus NB plus a n square by V kBT plus ln of g plus 3n by 2 ln of t, just like what we had in the earlier case. The last term is the same for both the van der Waals or dense gas and for an ideal gas, and therefore, if I am now interested in E bar is minus of dou ln Q by dou beta, that is minus of dou ln Q by dou T divided by dou beta by dou T, and that is again the first term will not contribute. The second term will give me minus of a n square by V kB T square. The ln g will not contribute because it is a function of n, and then you have plus 3n by 2 t divided by minus 1 by kB t squared. Again this minus minus comes together, and then you see there is some correction to the energy that is coming in the case of the dense gas, the correction with respect to the, if I simply had this, it was for the ideal gas. So, there is some additional correction that will come because of the additional interactions introduced in the hard sphere model or the van der Waals model. So, we can also go ahead and find the specific heat and so on, and this is pretty much tells me how, given a partition function, I can compute the properties. So, whole apparatus where I am finding the thermodynamic behavior remains the same irrespective of what definition of partition function we are using. Every partition function will give me a different equation of state naturally, but the way that we are doing the computation, the basic formula of the ensembles remain the same irrespective of the definition of the partition function. So, therefore, the broad objective, if I am interested in the thermodynamic behavior, is to find the partition function, and we have not so far discussed how to do that, and we will come to that later. But before we really go there, let us now think of couple other ensembles such as the grand canonical ensemble and the isothermal isobaric ensemble. So, there is something called the grand canonical or the mu Vt ensemble, which is pretty similar to the ensemble that we have been doing, the NVT ensemble, except the n is no longer a control variable, mu is a control variable. So, this refers to systems which are open, that is the number of molecules can change, but still at constant volume and temperature. So, if I think of the grand canonical ensemble, the way we think about it is still the same. We consider that we have an ensemble of some A states or systems and each of these A systems now have the same value of the chemical potential, the volume and the temperature. Although we can extend it to more than one component, in that case you will have a mu j here. I am right now doing it for only one component where there is only one chemical potential. We have been discussing that chemical potential is more useful when we have a multi-component system, but the basic derivation still applies. The simple extension will be that you will replace the mu with mu j of all the components. In fact, it can be somewhere in between where one of the component you are controlling the chemical potential and other component you are controlling the number of molecules. In that case, we can call it a semi grand canonical ensemble. One example is, let us say if you have a polymeric system with polymer and solvent, and polymer part of it is having the same number of molecules in every system, but the amount of solvent is changing in different systems. In that case, we can control the chemical potential of solvent and the number of molecules of polymer. That will be somewhere between the grand canonical and canonical ensemble, and that is referred as a semi grand canonical ensemble. But in this particular simple case, we are assuming that we have only one component and therefore, we have only one chemical potential. So, now in the canonical ensemble case, I defined Aj as the number of systems having energy Ej, but now both n and energy becomes a variable. So, therefore, now we will define the occupation as something like A and J, that is the number of systems with energy, and let me call the energy E and J, because now the number of molecule is also changing with the systems, and n molecules or in general particles. So, now there are two variables that are changing, what is the energy and one is the number of particles in the systems. So, now in this particular case, if I look at the summation over A, we have to sum over both the number of molecules and the energy levels of systems, and that will be equal to my total number of states in ensemble A. Also, if I look at the energies, we can look in the same way. We can sum over all the energy levels and all the number of molecules and the occupation number multiplied with energy of a system containing n particles, and that is the jth energy level of that. So, this is equal to again some constant E. The other assumptions remain the same. We are assuming that it is in an infinite bath such that the temperature is being maintained. The systems cannot still exchange energy, but the number of molecules in systems can change subject to the constraint that we have got here. So, finally, since the total system, we can still assume the mass is conserved. So, system plus the surrounding or the bath, the mass is conserved. So, there is one more constraint here, that is if I sum over j and n of A and j n, that is equal to some large number of molecule n. So, now we have 3 constraints, one for the number of state, one for the number of particles, and one for the energy of the systems, and all the constraints basically tells me that the total energy of the entire ensemble, the total number of molecules of entire ensemble, and total number of states of the entire ensemble is fixed in this particular system. So, what is going to be the number of ways of distribution in this case is like for a given distribution of A and J, we can think that the number of ways will be A factorial, and now for canonical ensemble we did a product over A J's, but now since we are doing a grand canonical ensemble, so therefore we will do 2 sums here, 1 over J and 1 over N, that is a product over all these factorials, and I can also replace the numerator with summation of J, summation over N, A and J factorial. And I can also write my constraints again. So, one constraint is for the number of states, the other constraint is for the energies, and the last constraint is for the number of molecules. And now the minimization problem is going to be dou ln W by dou Nj minus some Lagrange multiplier, the first constraint derivative minus some Lagrange multiplier, the second constraint derivative, and again some other Lagrange multiplier, the third constraint derivative. This has to be equal to 0 for all values of A and J. So, we have got this particular thing. So, let us first find the ln of W. So, W is summation of n summation of j A and J factorial. Note that we can always interchange summations, that is not really very important here. And now, if I take a ln W, I will have, using the Stirling approximation for large x, this can be approximated as x ln x minus x. So, this becomes summation of n summation of j A and J ln of summation of n summation of j A and J minus summation of n summation of j A and J. And now, for the denominator we have products of the factorials. So, if I take the ln, you will have the summation over the ln of that. So, you will have A and J ln A and J plus summation of n summation of j A and J. So, you will have cancellations, and therefore, if I do the dou ln W by dou Nj minus lambda 1 dou G1 by dou Nj minus lambda 2 dou G2 by dou A and J minus lambda 3 dou G3 by dou A and J. So, the first term is coming from here, and that will give me 1 plus ln summation of n summation of j a n j minus of 1 minus ln a and j, and then from the first constraint you will have minus lambda 1, the second constraint you will have minus lambda 2 e and j, the third constraint you will have minus lambda 3 n is equal to 0. So, if I do simplifications here, what I essentially will get is a and j is a exponential of minus lambda 1 minus lambda 2 e and j minus lambda 3 n. So, now if I look at this particular expression, there are few things we can notice here, that until the first and second part it bears similarity with the canonical ensemble, and actually the first lambda 1 we can get by using the constraint as I got for the canonical ensemble, summation of n summation over j a and j is equal to a. If I do this in this case, what I get is exponential of minus lambda 1 is 1 over summation of n summation of j exponential of minus lambda 2 e and j minus lambda 3 n. Pretty much the same thing as earlier, but now we have one extra summation and one extra term right here. And second thing is that since this pretty much refers to the same constraint as the canonical ensemble case, we can think of this lambda to be same as the beta, that is beta equal to 1 by kbt. We will see in the next class that it indeed works out correctly when we do that. The last constraint is a bit unknown here, so let me call it some gamma. So, as of now we have a and j at for the most probable distribution and let me use it like a and j star to indicate that this is already found by maximizing the w in this case, and therefore, this is already the most probable distribution. So, this is given as exponential of minus beta e and j minus gamma n by summation of n summation of j exponential of minus beta e and j minus gamma n. So, in the next class we will start from this particular point, and I will tell you how the properties are evaluated in the grand canonical ensemble, just like what we have done for the canonical ensemble. So, with that I stop here. Thank you.